Before we start this problem with a ginormous numerator, I want to write down an equivalency, which really is almost definitional with respect to congruence arithmetic. I'm going to write down A is a multiple of N. Okay. That reads, these are all integers, all right? And I'll do the double arrow for equivalency if and only if A is congruent to 0. We use these triple bars here. It's a form of equality that actually inherits a lot of the properties of division, is what makes it work actually. So A is congruent to 0 mod, and mod stands for modulo. Mathematicians are too lazy to write everything out. Abbreviations are prevalent, okay? So we're going to actually use this to solve this problem that involves a very, very large numerator. Now, note that 353 is prime, which turns out to be crucial. There's a very central result in number theory that makes this problem fairly easy as long as this is a prime number, okay? So let's move along. So you see what I've written up here says it's enough to show the numerator is a multiple of 353, right? Remember, this statement right here is absolutely equivalent to saying that 6 times 349 factorial plus 352 factorial is a multiple of 53. And a lot of you quickly recognize that what 352 factorial is, okay? I won't write it down, but I'm going to, the harder part is this piece right here, okay? Now we start out with a very well-known result called Wilson's theorem, and if P is a prime, this is true, and it's not hard to prove this really, okay? You can just pair up your multiplicative inverses, and then I think the one at the end is congruent, is its own multiplicative inverse. So you just, that's how it works. It's a very simple proof. Now, what we can do is this is just based on the definition of factorial. P minus 1, P minus 2 times P minus 3 times P minus 4 factorial is equal to P minus 1 factorial. But the thing that's really, really nice here is, remember, P is congruent to 0 mod P, right? That's very, it leads to a lot of equivalent formulations, okay, mod P. And that's a trivial observation there. Any integer is a multiple of itself, right? Namely 1 times itself. Okay, so you can see what happened right here. These P's became zeros, okay, and it's convenient to leave this P. We need some life to this thing. We need a corpus, right? And so we get this statement right here, which is just a rewrite of Wilson's theorem. But notice right here you would have minus 6 is congruent to P minus 4, okay, P minus 4. Now notice in this context, P minus 4 would be the 349 you see right up here, okay? So what you get is minus 6 times P minus 4 factorial. I'll just write down the result here. You'll end up with 6 times P minus 4 factorial is congruent to 1. And y'all, this has to do with, you may well wonder, well, look at all these minus signs here, you know. We have 3 minus signs here, so why do the minuses cancel? They cancel for the very same reason that if D divides A, then D divides minus A, you know. 2 divides 6, but it also divides negative 6, right? That's really why you can cancel minus signs when you're dealing with congruences, okay? But notice here that if we take P equal to 353, okay, we get 1 here, and then from Wilson's theorem we get minus 1. Well, gee, that certainly is congruent to 0, right? And so, done. I'll glorify it by saying QED. Okay, we proved it without even knowing the size of those enormous numbers. Okay, so again, a nice modular arithmetic proof that just rewrites Wilson's theorem in a favorable way. And you can rewrite Wilson's theorem so many ways it's ridiculous depending on what you want to do. It's just based on the definition of factorial, and the fact that p is congruent to 0. So you get a lot of rewrites. If you read Underwood Dudley's number theory textbook, he actually generalizes the way you can rewrite Wilson's theorem. Okay, and a lot of people just learn Wilson's theorem in that form, and then that's it. They don't stop and think that it has n other forms or something like that, n minus 1 other forms. And it's useful in terms of creating problems, and you find out who really understands this stuff. Even some teachers that I'm aware of take it at face value and forget that it has alternate forms, which creates confusion if you see certain types of problems, And I don't know of another way to solve this problem other than appealing to Wilson's theorem. Given the size of these numbers, you certainly can't do a compute and see if it's divisible by 353. You could consider factoring 352 factorial out of this, but you would end up with such a large number, or no, you could factor 349 factorial out, and you would have 349 factorial parenthetically times 6 times 350 times 351 times 352. And that number's too big to calculate. But that would be a quote a manageable number if you wanted to factor out 349 factorial and show that remaining piece of the factor was divisible by 353. Okay, so let me know if you think that's easier. I don't think it is. For smaller numbers, perhaps it's easier. For single-digit, double-digit factorials, it probably would be easier just to compute that number and verify it was divisible by whatever number you were interested in. But anyway, that is it, folks. So hope you enjoyed it.